Kepler laws. First law states that orbit of planets is an ellipse with the Sun in a focus. We already proved this result when we found the shape of the orbit. Note that if one of the masses is very large, then reduced mass is given by the smaller mass. Second law, planets sweep constant area per unit time. In other words, if we have the Sun and the orbit, of the planet, and we consider per unit time what sort of orbit chunk does it cover, it's going to be a constant area. Well, we can write the area element as just half of the distance squared to the planet times d theta for the element. Or in terms of dA dt, it's going to be half of r squared times theta dot. And using definition for the angular momentum, theta dot equal L divided by mu r squared, we get dA dt to be equal to angular momentum divided by 2 mu, which is a constant. The third law of Kepler states that period of planetary motion squared is proportional to semi-major axis to the third power. In other words, if we have the orbit, the Sun will be in the focus of this ellipse, and half of the major axis we'll call A, and half of the minor axis we'll call B. Then we can write that the period will be given by area of the ellipse divided by the aerial sweep velocity, or pi times A times B divided by the aerial sweep velocity that we just found, L divided by 2 mu. Let's prove this expression for a simpler case when A equals B equals R, circular orbit. We can write from the second Newton's law that mu v squared r is given by the force kr squared. From this we can find mu times v times r, which is just angular momentum, and it's going to be given by mu kr square root of. Next, we can substitute that into the expression for the period, and we get 2 pi r squared divided by k divided by mu square root of, and divided by square root of r, or 2 pi r to the power 3 over 2 divided by k divided by mu square root of. Remember that k is defined as g times m1 m2.